Hi everyone, this is a YouTube lecture for Chapter 7. It is about potential energy and energy conservation. As the content I've already previously posted is not well written, I rewrote the content, so you should take a look at the new version of Chapter 7 handout. What is potential energy? Potential energy is the energy which is stored in a system. There are several kinds of potential energy I like to introduce. First, the first diagram on the left shows a weight of mass m is lifted by a person, and when it is lifted from the ground by the height of h, the weight lifted vertically has a potential energy according to the gravitational force, and it is called the gravitational potential energy. There is a crane called the wrecking ball crane, which is used to destroy old buildings, and there is a huge mass m mounted on a crane, and if you pull this up to a certain point and release it, then the potential energy stored on the system can destroy a building. And another example of a gravitational potential energy which is used a lot is the hydroelectric power generator. If a water is stored at high position by a dam, by blocking a water flowing through a river, then the potential energy stored by the height of the water position can be used to generate electric power by rotating turbine. And that is the method to use to convert a potential energy to electrical energy. And there is a second type of potential energy. It is called elastic potential energy. But there are two examples I like to show. First one is the bow. Elastic potential energy is stored in a bow if you pull an arrow that is attached to a bow, and if you release it, it will the potential energy stored on the bow system will generate kinetic energy to a bow, the arrow connected to the bow. Now another example is electric potential energy stored in a spring gun. If a spring is compressed and if we put a ball just in front of a spring, and if we release the spring, we can generate kinetic energy which is initially stored in a spring. This kind of energy is called potential energy by elastic system. The third potential energy I'd like to explain is the chemical energy, which is also called the electric potential energy. It's the energy stored in the electrical force within a chemical composition. The first diagram shows the potential energy between electron and nucleus. As the nucleus is positively charged and electron is negatively charged, we can expect that there is an attractive force between electron and nucleus. And if the electron is removed from one position to the other, then the second atom at a different position of electron is called excited state, while the first one is called the ground state of an atom. And there exists a potential energy difference between an electron in an excited state and electron in the grounded state, and that potential energy is stored in an atom under an electric force, and this is called the chemical energy stored in an atom or in a molecule under the electric force. And the second diagram here is the diagram which shows the rearrangement of electrons and positrons within a nucleus before and after the combustion of methane. Methane is CH4, and if CH4 methane is combined with two oxygen molecules, 2O2, under a flame or spark, then it produces one carbon dioxide and two water molecules and a lot of heat. If 1 mole of methane is burned, then it generates about 800 kilojoule of energy, and we use this energy to run an engine or to heat a water and so on. And these are called chemical energy, but that is basically potential energy under electric force. So this kind of content will be covered in the second semester of the engineering physics when we deal with electric force. But here at the first semester, as we are mostly working on gravitational force, we'll deal with the gravitational potential energy in this chapter. There are several properties of potential energy. Potential energy is the result from a position or the configuration of a system. Potential energy is often written with U and is equal to the work you must do to move an object from a reference point to the position to a new position R. The important thing here is this is the work you provide against the gravitational force or electric force or any other force you are interested in. So I like you to make sure that this is the work done by you, not by the system. So I'll mention this point again later. And one of the interesting points of a potential energy is that you can put the reference value of a potential energy, which is U equals 0 point, arbitrarily. So the important thing here is not the absolute value of individual potential energy, but the potential energy difference, delta U, between one point to the other point. And as the potential energy is defined as the work you provide, its unit is has the same unit of work, which is the joule. So 1 joule corresponds to the 1 Newton of force times 1 meter of distance. So joule is a kilogram meter square per sec square. I'll skip this point, and now we are going to explain the gravitational potential energy. That is the potential energy under the gravitational force. So, as I mentioned earlier, the gravitational potential energy delta U is the work you provide to a system against the gravitational force. That means to overcome a gravitational force, Fg, you should provide minus Fg. So this is quite important point. To move an object from one point to the other. So delta U is defined as integral of minus F gravitational force and the distance you move from one point to the other. So if you consider in one-dimensional case, delta U is defined as minus from one point to the other of the integral of F with respect to distance. And F is a function of distance, you should integrate it. And in the textbook, delta W, gravitation, is defined as the work done by the gravitational force, not by you. When an object is moved same position R1 to the another point R2. So work done by the gravitational force is negative, oops, I should rewrite this one, negative of the gravitation of the potential energy. So I should put a negative sign here. So I'll change it before I post this one in the learner's homepage. So there are some examples in the textbook. If I move an object from Y1 to Y2 position, then there is a gravitational force downward, but I should provide a force upward to move this object from Y1 to Y2. So the work by the gravitational force is just the minus mg, that is the direction downward. So I put minus mg from y1 to y2 dy. So this is just a constant, so I just put the constant outside of the integral, and integral becomes y1 minus y2 because of the negative sign in front. And the gravitational potential energy, if y2 minus y1 is y, if we define y2 minus y1 is y, then this becomes minus mgy. So the gravitational potential energy is the opposite of negative sign of gravitational work done by the gravitational force. It is minus mgy. So U becomes mgy instead of minus mgy. So this is what it is. Gravitational work done by the gravitational force is the opposite of the potential energy. There is a concept called the conservation of energy. In this case, mechanical energy and the potential energy. So for a system, the total energy of a system 1 is kinetic energy of 1 plus potential energy of gravitational potential energy of 1, system 1, which should be equal to the kinetic energy K2 of system 2 plus the potential energy of system 2. As the kinetic energy is defined as 1 over 2 mv square, so we have 1 over 2 mv1 square plus mgy1, which is calculated just here. Potential energy is mgy. Then the second kinetic energy of the second system is 1 over 2 mv2 square, and the potential energy of the second system is mgy2. So this should be same unless there is a external non-conservative force involved. So the total energy we consider is the kinetic energy plus the potential energy, and that should be conserved in most cases we are dealing with. This is a this is related to the previous chapter, the work for a curved motion. If I mentioned before in the chapter 6 that if an object is moved from one point to the other under a gravitational force, the work done by the gravitational force does not depend on the path. So regardless of this path, unless there is a frictional force involved, the final speed of this object, it is obtained by as a kinetic energy is equal regardless of this path, whether it is fall from straight down or it has a curved path on a in an example of the pendulum or a curved a reclined slide. So we have already mentioned that regardless of the path, the work done by the gravitational force is identical as long as the initial height and the final height is same for two different cases. There are several examples. If we throw an object, if I throw a ball to this projectile, then the initial let's say from at the origin, if I throw a ball of mass m to this projectile and this projectile, regardless of the path, if the initial kinetic energy is given, then the kinetic energy at the same height should be the same. So regardless of its path, if the initial speed of this object is given, then the final speed of this object, regardless of its path, are all identical. And if the total energy at this given height is calculated, the total energy is same, but there are some kinetic energy and potential energy. If we calculate the energy at the peak position here for this projectile, then there is no kinetic energy along the vertical direction, while there exists only the potential energy at the peak position. Same is true for this projectile. If we cut this line at the height h, it is not at the peak position of the projectile, then there exists some kinetic energy as well as some potential energy. But because of the energy conservation, total energy should be identical. But here is another example. If a person is falling down with a skateboard at a position with zero velocity at the starting point, and if it falls by the height difference of h, then this person will gain kinetic energy while it loses its potential energy. It is defined by the height difference between this person and this person. So if it starts from the zero velocity at the initial point, then there is only potential energy, so total energy should be mgr if the radius of this curvature is r, and if it starts from the horizontal position of this circle, it is parallel to the center of the circle, and if this person is fall to the vertical position with respect to the center of this circle, then we can calculate that potential energy difference will provide a kinetic energy difference between this person at the top and the person at the bottom. And as there is no kinetic energy at the person at top, so we have the total energy should be mgr, and there is no potential energy at the bottom, so we have total energy equals to 1/2 mv squared. So we can calculate what is the final velocity for a given height r for this case. We can also calculate if this has a circular path, as we know the speed at the bottom in a circular motion, then we can calculate the acceleration with this. For a circular motion, acceleration A is equal to v squared over r. That's the important property of a circular motion. Because of Newton's law, force normal to the surface is equal to the m times the acceleration, ma. So that's the force due to the acceleration of the circular motion. And if we measure the normal force, it is n, then normal force is the force by the circular motion plus the gravitational force of this person, which is mg. So normal force is the force by the circular motion plus mg. That's the result we obtain. For a given radius, we can calculate v squared, and for given v squared and mass of this person, we can calculate the force by circular motion and the force by gravitational force. And if we add these two, then we can find the normal force. It is to the vertical direction when a person is at point 2. But in sometimes there exists a non-conservative force, which is often called the right. Sorry, this is a elastic force. The energy stored by elastic force. As I mentioned earlier, elastic force generated by a spring or a ball provide a force, and that force will provide potential energy. So for a elastic potential, we should include the potential by elastic force. And potential by elastic force is for a spring is 1/2kx squared. That is work done by a spring force. We have already mentioned this 1/2kx squared dependent work when we consider the spring at chapter 6. This is when only it is involved with elastic force, for example spring or ball, then for a spring then we can consider total energy is kinetic energy plus the potential energy of elastic force. If there is another force involved, another work or force involved, then we should include that as well to consider the total energy of a system. If there is another force involved, for example a resistance force or the friction involved, then we should consider the work done by frictional force as well, and this is the case when the energy is not conserved. This is the case when we throw a ball by ourselves with a speed, initial speed of V1, which is equal to 20 meters per second upward. If we throw the ball upward, we can calculate the peak position simply by using the energy conservation, which is kinetic energy times the potential energy for a initial condition 1 should be equal to the total energy at condition 2. Right. So by using this system, it is easy. We can easily calculate the peak position with respect to the initial position. If we call that peak position is y, then for system 2 at the peak position, that means V2 is equal to 0, then we have only gravitational potential energy, and at the bottom position where we have V1 is equal to 20 meters per second, and as we define Y1 as 0 point, then we have 0 potential energy. So we have the kinetic energy at the bottom equals to the potential energy at the top. So we can calculate the height difference between the 2 and 1 position, that is defined as y, that is equal to the 1/2 mv squared at the bottom position. So that's the use of the conservation of energy to calculate the initial and final height and velocity difference between the two systems. If there is a frictional force, for example air resistance or any other force, then the energy is not conserved. So we cannot use the conservation of energy law for a case with a resistance or frictional force involved. This example shows how much is the work done by frictional force. If this is the same case we consider for the example we have mentioned in this case 7.4. If an object instead of person is released at this point and it gains kinetic energy at the bottom, we can calculate the final velocity by using this simple equation. But we can measure the final velocity, and it turns out that if it is not equal, that means some energy is lost by frictional force due to the friction between the surface and the skateboard that person is using. So if we calculate, when we know the radius of the circle, and if we measure the velocity at the bottom by using the equation we have just explained, we can calculate final velocity. But if we measure the final velocity in realistic case, this velocity should be is frequently less than the velocity we obtain. Then we can calculate the kinetic energy difference between the ideal case and the case we have measured. Then we can calculate the loss of the energy due to the frictional force. That's what it mentioned. Same is true. If we throw this, if we throw an object with a slide with the frictional force, if we throw this one, and if there is no frictional force, it will return back its the original position with the same speed. But if we measure the returning speed at the initial position, if the speed is, for example, 4 meters per second, then we can calculate how much is the energy lost by frictional force between the surface and this object. So that's what it is, what it explains. This is the second part of the chapter 7. So far we mentioned about the gravitational force and the gravitational potential energy related to the gravitational force. Here, if we ignore the gravitational force and friction, if there is only a spring force involved for this object, and if we displace this object by a certain distance, x1 or x2, then there exists a potential energy involved with the elastic force by the spring. And that is called elastic potential energy by a spring. Work done on a spring the force by spring is k times x. That's an important property of a spring. If we integrate k times x with dx, we have 1 over 2kx squared. And the work difference between point 1 and point 2 is just a 1 over 2kx2 squared minus 1 over 2kx1 squared. That's the work done to a system when we move an object from x1 point to the x2 point. So the work done by the spring is calculated as the minus 1 over 2k2 squared minus 1 over 2k1 squared. That is defined as the minus delta potential energy. So the potential energy, if x1 is equal to 0, for example, then the potential energy is 1 over 2kx squared, and that can be displayed with the quadratic function of x, and this is the position dependent potential energy for a spring whose spring constant is k. Because of the kinetic energy and the potential energy sum is the total energy, if we have a potential energy, if it looks like this, the kinetic energy will be the opposite shape of this one. So if we add the kinetic energy, if it looks like this, and the potential energy, if it looks like this, then that should be constant. That is what it is. The total energy should be potential energy plus kinetic energy. It should be constant. So that means kinetic energy has the opposite sign of this one, plus a constant. So that's the property of a total energy for a spring. If an object is under a gravitational force as well as electric force, we can calculate the total force involved with the system by adding the gravitational force plus the frictional force. That's another example. This shows the conservative force and non-conservative force. Conservative force is the gravitational force, frictional force, and electric force, and so on. The non-conservative force is the path dependent, it is the frictional force, resisting force, and so on. So, non-conservative force will provide a dissipative work that provide heat. For example, frictional force provide heat, and sound, for example. If there is a frictional force between an object on a surface, it may provide heat as well as sound. And so the energy is lost to the heat energy and sound energy and so on. The energy conservation state that kinetic energy and potential energy and the internal energy, here we didn't mention about internal energy, but internal energy is frequently known as the chemical energy, and the chemical energy or temperature, heat, and so on. So the internal energy plus kinetic energy plus the potential energy is constant. So that mentions the conservation of energy. Right. As we have previously defined, the delta U potential energy is for a one-dimensional system is minus from one point to the other the force under the system dx. For a gravitational force, we have a force. We should provide the force against the gravitational force, so that should be negative sign in front, and that's the definition of potential energy we provide to a system. And from this relation, left side is the potential energy and right side integral of the force. That means if we take a derivative on both sides, then the derivative of potential energy should be equal to the minus of the force. So the force is the minus of the derivative of potential energy. So that is the important property. It can be easily derived from the definition of potential, because potential energy is a negative of a force dx. So if we take the derivative on both sides, we naturally obtain the force should be negative sign of the derivative of the potential energy. So we mentioned that potential energy of a spring looks like this, and if we take the derivative of this one, then it becomes like this. But if we take a negative sign, then it is flipped, and so the negative, so force with respect to x is negative when displacement is positive, or the force is positive x direction when the displacement is in the negative direction. So that's what it is. For gravitational force, potential is mgy or mgy. So if we take the derivative of linear function of y, then we have a constant. So that's the force, which is minus mg. Right, so that means the force is along the negative y direction. We'll skip this one. And so the force is the minus of the derivative of potential. That's what it is. This is from the definition of potential with respect to force. For example, if this is a gravitational potential, then the gravitational force is negative of the derivative of gravitational potential. Right. That's about chapter 7, and we'll cover chapter